So my name's Rebecca Gray. I'm at Lancaster University. I finished my PhD 3 years ago. It was in space physics, so that's quite different to what this talk's going to be about. But for the past 3 years, I've been on this project looking at radiation damage in HTS tapes with a particular application in fusion reactors. And what I'm going to do in this talk is introduce the HTS tapes in the fusion reactor application. I'm going to talk about why radiation damage is a problem for them. And then I'm going to show you the model that I've made that seeks to understand how radiation damage is damaging the tapes, and then show you some of the results for it as well. So first off, this graph here shows us various technologies over time and their operational temperature. ITER, which is the European flagship, uses niobium tin down here. But this talk is focused on HTS tapes. We're using REBCO, which is this material here. You can see it operates at a higher temperature, so we don't need the super cooling systems. But more importantly, when we wind the HTS tape onto a coil, we can access extremely high field. And therefore, it's been considered by some people, Tokamak Energy for one, to be a game changer for fusion. This allows us to make our fusion reactors more compact with a much lower aspect ratio. And as I say, runs without the supercooling system. Now, this being compact is important because as your fusion plasma is going around, it's going to be giving off these neutrons that are very high energy, 14 MeV in some cases. And we need as much room as we can for shielding from those neutrons. The way those neutrons will damage is they'll come in, they'll interact with parts of the magnet in this case, impart energy to the atoms, displace them and begin a damage cascade as the atoms knock into each other. And we're seeking in this project to see how those cascades develop. So what do we know from the literature? Well, a previous experiment in 2018 in Vienna from the trigger reactor showed at 360 K, there's initially an increase in flux spinning centers, and that means that there's an increase in JC. But JC then falls with increasing damage. Secondly, we know that oxygens are thought to dominate as a result of radiation damage in this material. And thirdly, we know that the CUO plane is really important for superconductivity. And those three things lead to a couple of questions. What is it that's causing these flux spinning centers on the nanometer scale? Is it, as I've suggested, that the atoms are displaced, they crash into other atoms and you get these amorphous regions? Or is it something else? And when JC begins to fall, is it because the flux spinning centers have saturated, or is there some other kind of underlying damage going on? And it's those two questions that form my first big research question for this project, which is how well do the tapes withstand neutron radiation damage? I'd also like to know what happens to the oxygen defects, because we're concerned about how they're moving around, particularly that CUO plane. And then thirdly, it's very easy for us, or not easy, but easier for us to do experiments at 360 K to test how the tapes hold up to radiation damage. And at 360 K, they do show some annealing. There is enough energy, thermal energy, for those atoms that have been displaced to find their way to either like sites or their own sites and therefore heal. But at 25K, how much of that is actually going to happen? Is there going to be enough thermal energy for atoms to move back to sensible sites? Well, why not do lots of experiments instead of looking to simulation? Well, as we all know, experiments can be quite hard and long to do, but with atomistic simulation, once you've got your model up and running, and I appreciate it's taken me 3 years to get a model up and running, but once you've got that model, you can do lots of different experiments or simulations very quickly. But more importantly, radiation damage is happening on the nanometer scale, and we're really seeking to understand what's going on of the physics on that scale. And therefore, it's a really good tool for us to look in this nanometer scale. Now, the particular flavor of atomistic simulation I'm using is molecular dynamics. And this is where we advance a system based on Newton's law, F equals ma. We know the mass of the atoms, and we know the acceleration because we're going to use a potential, which I keep referring to as my model, to describe that acceleration. And therefore we know F the force. And that allows us to track the velocity and the position of all atoms at any given point in time. we can control the number of atoms, the volume, the temperature, and the pressure in various different ensembles. And to give you a flavor of that, I've got a little simulation here where I'm controlling the number of atoms and the temperature. And what you can see is a change in the volume and the pressure there. Now, there does already exist a potential for this material. It was developed in the late 80s by Stephen Chaplot, and it's a really good potential. It is fantastic. It's got these first three terms here, the Coulombic term here, this repulsive term, and this van der Waals attractive term. And those first three terms, they all interact between every type of atom and every other type of atom. Apart from this fourth term, and this is where we've got a bit of a problem. This fourth term only interacts between coppers and oxygens either in the chain network at the bottom of the unit cell or in the plane network in the middle of the unit cell. And let me illustrate that. It's either coppers and oxygens in this chain down here or in the plane up here. Now that's a real problem for radiation damage simulations, because what happens if I take this copper 1 down here, I displace it and I put it up in this environment here? Well, as it stands, it's going to remember its previous interaction with the oxygen and interacts with the oxygens up here in the previous way, and that's not right. I've dubbed this the memory problem. So what we need to do is to develop a new potential that treats every single copper and oxygen type the same as before. And that's what the first step of my project outline is to develop an empirical pair potential. It's empirical because I'm going to fit it to data. But we then need to validate that pair potential, and we do that with the displacement energy of the atoms. That's a really key parameter for radiation damage. Radiation damage is all about knocking atoms off of their sites. So we need to make sure that the energy to do that, the displacement energy, is physical. And I'm going to show you that in this case for this model it is. And then thirdly, once those atoms have been moved off of their sites, they're then going to evolve within the cascade. And we want to know what kind of defects are created and do they heal. We want to know all about those kind of cascade dynamics. So first of all, the potential. Well, we're using an idealized REBCO structure. We're going to use the first three terms that Chaplot did, which is the repulsive term, the van der Waals, and then the Coulombic term here. And then we also need to consider the nuclear forces. If I've got two atoms and I push them together, we know actually then they're not going to meet. Unless we're actually fusing them, we don't want to fuse these atoms. They're not going to meet. So we need to introduce another term there, which is the ZBL spline, and that's acting as a hard wall to stop the atoms from meeting. Now for each atom pair, I can determine A, B, and C, and then the charges Q1 and Q2. I'm going to choose a set of that A, B, and C. I'm going to run a simulation to see what properties and structure develops. I'm going to check that against what we see in experiment or in other data. And if it's a good fit, great, we'll keep iterating with that particular set. But if it's a bad fit, we chuck it out and start again. Now the program I'm using to do that is called pProfit. It's been developed by Michael Rushton at Bangor University, and it is a fantastic bit of kit, it really is. But it's important to note that we're working with an incredibly large parameter space. I've got 10 different interactions with 3 different parameters, so that's 30 independent variables. And then on top of that, I've got the charges that I can choose as well in the Coulombic part. So that's at least 34 different independent variables for REBCO. A very complicated parameter space. But I've got a great tool at my disposal. I've got the global optimizers. I can use genetic algorithms and particle swarms. I can also use the local minimizers as well, like the Nelda-Mead simplex. And at this point, as I set off on this fitting journey about 3 years ago, Michael had some advice for me. He sat me down and he said, Becky, do not just use your fitting powers in anger, but fit to as much physics as you can. And that's informed my fitting strategy outlined here. There are lots of things that we can fit to. We've got the lattice parameters in A, in B, and in C, the length of the unit cell. We've got how those change with temperature, the thermal expansivity. We've got the elastic constants, the stiffness, and then the melting temperature, diffusivity, and various energies. But I've got a decision to make at this point. What am I going to train my model to? What's going to be in my training database? And what am I going to use to test my model? Well, I've chosen to use these top 3 as the training and then the bottom 4 as the test. And the primary reason I've done that is because these simulations up here, they're very quick to run, which means I get more bang for buck in terms of fitting time. I've got another decision to make as well. What weightings am I going to set for each of these properties? Am I going to say it's really important that I get the lattice parameters bang on? Or is there going to be another property that I think is more important? I get to make that decision. And this leads to the larger point that actually all models are a reasoned compromise. There are some things this potential is going to do really well, and some things it's going to do slightly less well. I get to make the decision as the designer as to what those are going to be. And I think as long as I know the weaknesses as I look at the results, that's okay to do. So let me show you how well the model performs. I'm going to go through this section a little bit quickly because I think it'll be slightly less interesting than what's to come. But these are the thermal expansivities. In the red, we've got the DFT that we fit to. This was generated by my supervisor, Samuel Murphy, came out in a recent publication. And in blue, we've got REBCO 18, which is what I've called my potential here. I've also plotted in yellow the chat plot potential as if you were going to take that fourth term and just blanket apply it to every CU and every O. Now, that's not the way I think chat plot intended the potential to be used, but I have seen some research groups doing that. So I'm going to use that as a benchmark as we go through these validation steps. So this is the A parameter. This is the B parameter. And this is the C parameter. And you can see REBCO 18 sticks within the error bars of the DFT fairly well. Onto the elastic properties. I've broken this down into its matrix elements. I'd like you to note that the DFT here, which comes from Sam's data, is fitting very well with the experiment over here, fantastically well. But this actually shows one of the first, one of the main weaknesses of my potential, and that's that the bulk modulus of my potential is only 93 GPa, whereas the DFT predicts 110 GPa. So we know that the potential that we've got is a little bit soft, not very soft, not problematically so, but just a little bit soft. And we bear that in mind as we look at the results. Onto the big validation parameter, the threshold displacement energy. Now, this is the energy that you've got to give an atom in order to create a defect. And it's not necessarily going to be the atom that you give the energy to that itself will become the defect. It could be another atom, as I'll show in the example here. So in this example, I'm going to take a copper in this region here and push it into the page in the Y direction. And what you're going to see is a little oxygen pop out to the side and form a stable defect. So I've moved my copper back. My oxygen in red has popped out to the side. The rest of the cell is returning to equilibrium around it. But that oxygen there has now formed a stable defect. I've overcome the threshold displacement energy there. So which one was that? That was the copper one in the Y direction, so that's here. And you can see that I've tested each type of atom site in each of the directions. Now, ideally, this would be a much larger, statistically significant study. I would do every degree of angle, and I would do them multiple times. But this is what I've had time to come up to do at this point. I'll look to expand this. In green, I've put the lowest threshold displacement energies there. So these are the thresholds and the directions in which they occur. What's nice about this is that I can see the copper, by and large, have a much lower threshold displacement energy than the barium in the yttria, with this spurious exception here. And that's physically correct because we know that the mass and the charge of the yttrium and the barium are large, and we'd expect them not to move. So this shows us that our potential's behaving physically. Even more happily is what's happening with the oxygens. Now, previous work has been done and has shown that the TDE for the oxygens is between 4.2 and 18.8 EV. And most of our data sits within that range, so I'm very happy with that. But what's nice is that that previous potential assumed different interactions between the coppers and the oxygens at the different sites. So because we're seeing agreement with that, this is telling me that actually my assumption that the coppers and the oxygens have the same interaction everywhere, actually that stands to reason. That doesn't affect the threshold displacement energies. What's also nice about this is that the oxygens in the O1 and the O4 sites, which appear in the chain position, have a lower threshold displacement energy than that in the O2 and the O3 in the plane. And this suggests to us that we might see more chain oxygens becoming defects than the inner plane. The final parameter I want to show that we get right is the oxygen diffusion. And it's important because once we've moved our oxygens off the sites, they're going to migrate through the crystal, and the activation energy tells us about the barrier to that movement. Now in the bulk material, it's 1.1 to 1.3. REBCO 18 gives an activation energy of about 0.75, which is a little bit lower than I'd like. However, it's better than any other potential out there at the moment. So let's move on to radiation damage simulation. How do these simulations work? Well, what we do is we simulate that a neutron has imparted energy, given energy, to a pKa. That's our primary knock-on atom, and that's the red atom here. In this case, it's given it, and the barium is going to move in this direction. It's a barium pKa, and it's going to move with a 5 keV in the Cascade region. It's going to hit other atoms. Now, outside of this region, we've got the pseudo-Langevin boundary, which is a heavily thermostated region. And what this is ensuring is that if I've got atoms colliding on the very edge of my Cascade region, what can't happen is atoms come out, hit a wall, and then come back in, because they'll be slowed down by the thermostat. That won't happen. And that's important because that's how we get around the fact that we're trying to model a very, very large bit of crystal in a very, smaller region. So what might we expect? With a radiation tolerant material like UO2, which is quite a simple unit cell here, this is what we'd expect. Initially, you get these hot spots where there's lots of disorder in the red, and this dissipates out as atoms knock onto each other. And then there's this dissipation. We get the forming of these point defects as the energy knocks more atoms off, and then we get the recombination here. So we're left with some point defects and some small amorphous regions. So initially we've got the hit of energy, the energy is dissipated, and then we begin the recombination process of atoms finding like sites or their own sites, and we're left with just a few point defects and a region of more disorder or amorphous region. What would that look like on this kind of graph? Well, here I'm plotting the total number of defects versus time, and you'd expect and the initial hit of energy would give you lots of defects, but eventually those would recombine, and you'd be left with not so many defects by the end, a low level of residual defects. And what might we expect with the two temperatures? Well, at 360 K, there's more thermal energy. Perhaps our atoms are a little bit further apart. There's more room and more energy to do damage. So there's initially more damage. But actually, because they've still got that thermal energy, they can go and find their like sites or their sites, and they can recombine and end up with lower overall defects than the 25K case. That's our expectation. Well, let me tell you now, REBCO is not a radiation tolerant material. It's going to defy each of those expectations. So let's take a look at a cascade. What you're going to see is every atom that's being displaced. And you can see initially the atoms are knocking into each other. We're getting a large area of damage. But then we get these features here emerging. These are constrained in the z-axis, and actually you can see they're kind of periodic. And we can also see, because of their color coding, they are blue and red. So these are coppers and oxygens. And we also see small amorphous regions here. So this is quite different to the expectation we did have. What does that look like when we run it at the two different temperatures? Well, initially we do see more damage at the 360, which is what we expected. But because we're not getting as much recombination, actually that damage level stays remnant compared to that at 25K. This is the opposite of what's seen in simple crystals, but actually it might not be too bad news for the fusion community. This graph is implying that if we did experiments and found that our tape stood up to radiation damage at 360K, then actually when we take them down to operational temperature, there's not going to be any extra damage. In fact, the damage might be lower. So we can use the experiments as a good benchmark. Well, what is it that's actually driving the damage? Well, on the left-hand side here, I've shown you where every atom has moved away from its site. And on the right-hand side, I've shown you where it's moved to. So which atoms have now got an extra atom near them. This is predominantly red, which means its oxygens are on the move. Brilliant, because that's what the literature suggested before. The question now becomes, well, where have the oxygens come from and what are they doing? What are their movements? Now, the way I've gone about analysing that is to take our supercell and fold it back in the X and the Y and in the Z onto its original unit cell. If you ignore the right-hand side for a second and just look at the left-hand side, we've got our original unit cell here, but I've also indicated with these grey spheres where the likely interstitial positions might be. So they are the 1, the 2 on the bottom chain, the 3 and the 4 around the barium, and then the 5, 6, 7 around the yttrium. What you've got on the right-hand side is the output of a cascade. And you can see we actually do have a lot of oxygens that I've coloured them white so that we can see them, but they are the oxygens appearing in this 1,2 site. So our question is still, actually, where do these oxygens come from? Are they coming from the chain? Are they coming from the plane? Remember, if they come from the plane, I've got concerns about the superconductivity. So what I've done now is I'm going to show you the cascade occurring in this folded view and look out for the white spheres, where they come from and where they end up. Initially, everything's quite nice on its home site, but as we ramp up the temperature in that cascade, everything's moving away from its site up until this point of maximal damage. And I can see the oxygens are starting to appear at that site down there. Now, as the temperature fades away and everything's beginning to recombine back to its sites, actually, these interstitials, they're quite happy at their new site. That's now a stable defect down there. So we're forming these interstitials in this position. On the left-hand side here, I've got that final frame. What I've done is I've isolated those, what I've called O5s, those interstitial positions. And then between here and here, what I've done is I've wound back the clock to find out where those oxygens came from. Now, I would love to be able to tell you exactly what percentages of the oxygens are coming from which sites, but I can't do that yet. This is a sort of like mid flow of my investigation. But if we're going to believe what the TDE was showing us, what the threshold displacement energies were saying, we'd say actually it's likely to be that there are more coming from the chain positions down here than there are from the planes. Let me show you my second to last result. Our crystal is very anisotropic. We might expect, therefore, that if I'm launching atoms in the X direction compared to the Y or the Z, we get different amounts of damage being done. However, this graph here is showing us the data at 360K and the data at 25K at the various X, Y, Z directions. And I don't think you can look at this and say, oh, one direction is particularly damaged. I don't think you can say that from looking at this graph. They're about equal levels of damage. That was with a barium pKa. Let me now show you what happens with the yttrium pKa by imposing the data on top. Again, same story. It's not directionally dependent, this damage. Now, the caveat to this is that this is just 30 cascades of data. I've just not had time yet, having finished the model, to begin looking at much larger scales, but it'd be interesting to see whether this result is robust. And that leads me on to my last slide. Everything I showed you in this presentation so far is contained in this data point down here. This is the energy of the primary knock-on atom, so the amount of energy we're simulating the neutron giving to our knock-on atom compared to the total number of defects it creates. And as we'd expect, you hit harder, you create more defects. That makes sense. It's got this linear relationship. Now, all the experiments are working at about the 50 MeV to 100 MeV sort of scale. And I would love to be able to, in the next few months, ramp up the energy and the size of my cascades to find out just how much damage we're doing and whether this linearity seems to continue. So as I've said, I'd love to bridge up to the higher energies and meet up with the physical experiments. I also want to find out what's driving these new interstitial positions, where are the oxygens coming from, and what does that imply for the superconductivity. I also want to talk about, well, think about these amorphous regions. I've not talked about this very much in this presentation, but actually at the beginning I kind of implied that the flux spinning could be to do with the amorphous regions. So it's important to know how big those are and how they scale with the amount of energy you're imparting to your cascade. And then finally, this has all been done with a pristine crystal. But we know that the manufacturers put defects into those tapes. So what would happen if I reran this analysis with a pre-defected crystal? Well, with that, I'd like to thank my funders. I'm funded in part by Tokamak Energy and the EPSRC. and to thank Archer, whose computers I've been using. Thanks very much.